Hello, everyone. I'm excited. This is our last exam review video of the semester, and I have enjoyed this semester so far. You guys have been some of the nicest students that I've ever had in this class, and it has resulted in me just having a great time teaching. So, let's address the elephant in the room. Exam 4. This is going to be our last exam before the final, and in my truthful opinion, this is the exam that I struggled with the most, and it's truly because I was not good at balancing equations. So, what should you do? Practice, 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 practice. And I mean, look at the workbook, do some ALEKS problems, go find some workbooks online. With this, you should gain a good handling of balancing equations. Specifically for this exam, I could balance equations, but it just took such a long time for me to balance them that I basically ran out of time for these exams, and I'm usually a quick test taker. So, again, practice, practice, practice. I really don't have any announcements outside of the Canvas announcement that I will not be having office hours Monday and Tuesday due to dental school interviews. I apologize if that has caused any inconvenience. Please send me an email if you have any questions about this video, or if you want to meet up sometime throughout the week, please send me 3 specific times that work for you, and we can see if that works with both of our schedules. Okay, so at this point we should know how the exam procedure works, so I'm just going to brush over that and dive straight into some stuff that I would write down on my exam information sheet before the exam starts. Specifically, I would write down the dilution formula, which is you have a concentrated solution with a certain molarity and certain volume, and we dilute it to make a certain concentration and a certain volume of our dilute solution. Also, I would write down basically an annotated short note version of our oxidation state rules. So hydrogen +1, oxygen -2, group 17 elements -1 within a molecule. Pure elements are going to be 0. Ions are going to equal the charge of ions. The oxidation state will equal the charge, and the overall charge of the molecule will equal to all the sum of the oxidation states in the molecule. And this little e thing, that is the sum, or a mathematical way to say that. Alrighty, so as I always say, start with the free response questions. However, for this exam, there might be an instance where you look at a question, cough cough, question 20, that will take you a significant amount of time, either because it's a really difficult stoichiometric balancing, or you just blank on the question, and that's totally valid. Identify that as quick as possible and move on. Then, once you're all done with the questions that you know, come back to those questions and go from the easiest to the hardest. Alright, so for question 19, we are basically identifying which reaction is going to be redox, acid-base, or precipitation. So for redox, that's going to be a change in oxidation states between the products and the reactants. Acid-base, that's when an acid and a base come together to form water and some form of salt. And a precipitation reaction is when we introduce 2 solutions, aqueous solutions, with each other, and usually that will result in a formation of precipitate and some spectator ions. Alrighty, for this first reaction, I see H2O liquid. Immediately it's running through my mind, this is acid-base reaction. Furthermore, I see hydroxide and I see hydrogen. So if we're writing our net ionic equation, the hydrogen and the hydroxide ions are going to form together to form water. All is to say, this is an acid-base reaction. And it's not a precipitation because I do not see any precipitate being formed within the products, and we also have water in the products. Now, for this last one, you can use the process of elimination or check the oxidation states, but this is going to be a redox reaction. I see that all of these products and reactants are all solid. For a redox reaction, that can happen with all solid. For acid-base and precipitation reactions, that, for the purposes of Gen Chem 1, that's not going to happen with solids. So immediately, it's going to be redox through the process of elimination. And then if you look at all the oxidation states, this copper will be +1. The silver will also be +1. This is going to be -2. This is going to be 0 because this is in a pure element form. And then, as always, oxygen within a molecule is going to be -2. And there may be a question that asks which one's oxidized, which one is reduced. Look at the oxidation states and remember that electrons are negative. So if something becomes more negative, that means it's gaining electrons. On the opposite side, if it's losing electrons, it is becoming positive. I meant to put a positive here. That's my fault. So in this instance, copper is getting oxidized because it's becoming more positive, while silver is reduced because it gains that electron and becomes more negative. All right, number 20. Briefly mentioned this right before we started this. This is the one that I would probably skip over because this one is frankly a quite difficult balancing equations. My tip for this would just to identify one element in the reactants and in the products that can be easily balanced. In this case, I see sodium, and there's only one reactant and one product that have sodium in it. So whatever coefficient we have here is going to be directly correlated to this coefficient. So immediately just balancing, this should be a 2. And then after that, I'm going to keep track of everything. So we have 2 sodiums, you just balance that. We have 4 phosphorus, 2 phosphorus, sulfur, we have 2, 3 sulfur. Yep, 3 sulfur, 3 sulfur. Hydrogens, we have 4. Hydrogens, we also have 4. Alrighty, so that is basically everything besides phosphorus to balance. However, I would heavily recommend just picking one of these and throwing a number there and then going to add another coefficient to the other product to balance everything out. So for this one, I'm just going to throw, let's do a 1 right here. Now, let's keep track of everything. Sodium is becoming 4, which means that we should keep this ratio of the sodiums. This should be a 4 now. Phosphorus, we still have, I meant to write a 2 here. Not a 1. Phosphorus, we have 3. Hydrogens, we have, or sulfurs, we have 6 here. Phosphorus or hydrogens, we have 5. Now in the product side, I have 4 sodium. Phosphorus, we still have 4. Sulfur, we have 4. We have 5 sulfur. Hydrogens, we have 2, 4, 6. Alrighty. Now I see 3 places that we can go. I see the sulfur and phosphorus that can be easily balanced. Since we already did a phosphorus here, let's just put a 2 right here just to see how that affects everything. I'm going to write this in pink. So now we're only affecting the hydrogen amounts for everything. So sodium, that's going to stay the same for both sides. Phosphorus, this now becomes a 4. Phosphorus in the reactant side still stays as a 4. Sulfur, we didn't really touch sulfur, so this still stays as 6. This still stays as 5. Now hydrogen, we have 6, 8, and this hasn't changed. Alrighty, so now our phosphorus and sodium are balanced. Now we're only really concerned about the sulfur and hydrogen. Specifically, we don't have enough in the reactant side, so our only way to compensate for that is to add a coefficient here. And since there is 1 sulfur and 2 hydrogen, if I add a coefficient of 2, this now becomes 8, this now becomes 6. Nothing else changed in the reactants. This is still 4, this is still 4, 4, 4, 6, 8. Everything's balanced. Now, if this was me taking the real exam, again, I would skip this question personally, because this one took me a while to figure out a way that works. So, all condensed into one big lesson. Start from the easiest element to balance, and then just slightly add more coefficients just by ones at each time. If I went back and had that 2 with the sodium and 1 with here, and then I saw that, oh, maybe I can add a 3 to balance out the phosphorus, we would go down a rabbit hole that would take a while to get out of. But since we did it incrementally, one by one, and took our time with it and broke down all the amounts of each element, we slowly yet surely got to our solution. Alrighty, question 21. We got a balanced reaction here. We got 9 grams of hydrochloric acid with sodium sulfite with this liter in molarity. What is the theoretical yield of sodium chloride in grams? And remember, sig figs apply here. Alrighty, so first, let's just find our limiting reagent. Easiest would be hydrochloric acid. So we're starting with 9.8 grams of hydrochloric acid. And let's calculate this real quick. I get 36.458 grams of hydrochloric acid is going to be 1 mole of hydrochloric acid. Then, from there, we use our stoichiometric ratio of hydrochloric acid to what we're looking for, which is our salt, NaCl. So it's basically 2 for 2. If we have 2 HCl, or 2 moles of HCl, we get 2 moles of NaCl. Alrighty. Now, since we're looking for grams, I'm just going to convert everything into grams. In 1 mole of NaCl, I have my periodic table with me in person, so let me just calculate this real quick. All right, I get 58.44 grams of NaCl. I'm throwing this in my calculator real quick. All right, I got 15.708 goes on for a while grams of NaCl. Now, just a reminder of my little tip about using a calculator in this exam. Multiply all the numerators, multiply all the denominators by each other, get that number, and then take the numerator divided by the denominator, and that will be the easiest way to ensure that you don't have any calculator error when doing large dimensional analysis equations. It also is slightly quicker from my experience. Alrighty, now let's figure out how much sodium sulfite generates. So we're starting with 0.040 liters of sodium sulfite. I'm just going to abbreviate it as SS because that takes less time. And this is one of the questions that you don't have to show all your work, so abbreviating it as SS is totally valid if you know what that abbreviation means for you. Then, to figure out the amount of moles of sodium sulfite, we use the molarity of it. So if we have 1 liter of solution, or 1 liter of sodium sulfite, that's going to have 2 moles of sodium sulfite. Then we use our stoichiometric relationship. We have a 1:2 ratio. So 1 mole of SS is going to generate 2 mole of our product. I'm just going to write P for time's sake. 1 mole of our product, or 1 mole of our sodium chloride, is 58.44 grams of our product. So, throw this in a calculator real quick. I get 9.3504 grams of sodium chloride. Alrighty. Per our definition of a limiting reagent, the sodium sulfite is going to be our limiting reagent, which generates 9.3504 grams of sodium chloride. However, we always have to look at our sig figs. So, just looking at our sig figs for this one, I see 2, infinite. Well, this should be 2 sig figs. I didn't write the 0.0. This should be infinite. This should be 4. So based off our multiplication and division rules, this should be 9.35. Cool. Going on to question 22. Sodium hypochlorite, commonly known as bleach, can dissolve in water, form a highly corrosive solutions at high concentrations. Due to these parts and properties, bleach is commonly used to whiten clothes. The maximum concentration of bleach found in fabric, safe cleaners, is typically 0.13 molars. You buy 2.4 liters of a 0.16 molar bleach solution at Target. Calculate the amount of 0.13 solution that you can make. Report your answers in liters. Alright, this is our classic dilution equation. So we have the MC, LC equals MD, LD. So we started with our concentrated solution. We're buying it at target, and we're trying to dilute it to that 0.13 molars. So MC, LC, we already know that. And we're trying to find LD. So algebraically, MC, LC divided by MD should equal LD. And I'm just going to just plug in our variables. So MC, that's going to be our 0.16 molar. Then we have 2.40 liters of that concentrated solution. Then we're just trying to make 0.13 molars of that diluted solution. Throw this in the calculator real quick. I get 2.95, goes on for a while, and by sig fig rules, we're going to have to round this up to 3.0 liters of our final solution. And always for these free response questions that you show your work, please box in your answers so Dr. Outlaw has an easier time grading these questions. Alrighty, last final free response question. So we have hydrosulfuric acid with an unknown concentration, takes a certain amount of liters and concentration of our base to neutralize a 20 milliliter sample of that hydrosulfuric acid solution. And we're just determining the molarity of that acid. So all is to say, this is one of our neutralization reactions. In a neutralization reaction, an equal amount of acid and base react with each other to completely neutralize each other. So when I'm looking at these two things, I wrote down the formula. Let's just balance it real quick. I see we have two hydrogens. This is diprotic acid. We need two hydroxides to make two waters. Everything else is balanced from that. And just a general tip for balancing acid-base reactions, I really only look at the hydroxides and the protons and balance those and just throw whatever amount of water we make right here. And usually after you do that, the entire equation should be balanced. You may have to throw another coefficient here just to keep the amount of elements in the reactants consistent with the products. But in this case, we don't have to worry about that. Alrighty. So, starting a neutralization reaction, we know that we start with all this base with a certain amount of concentration, and it neutralizes this amount of volume. So, let's start with the amount of base. Use the stoichiometric ratio to figure out how much hydrosulfuric, how much moles of hydrosulfuric acid reacted with our base. And then from there, we know that we have 20 milliliters of that hydrosulfuric acid. So whatever moles we get from finding out how much of our base reacts to that, divided by our liters, that should give us what? Molarity. Alrighty, so 25.25 ml of NaOH. Then we're trying to convert it into moles for stoichiometry purposes. So the given concentration, is 9.9 moles of NaOH per 1 liter of solution. The issue here is that we're given things in milliliters. So 1 milliliter is 10 to the negative 3 liters. Then we can throw in that to figure out the amount of moles, and then the stoichiometric ratio. Two sodium hydroxides are going to react with 1 hydrosulfuric acid. So in the mole ratio for that, 2 moles of our base is going to react with 1 mole of our acid. Alrighty. Let me throw this in my calculator real quick. Alrighty, I got 0.12499 mole of sulfuric acid. And I'm going to highlight this 2 because I see that we have 2 sig figs here, and that's the lowest amount of sig figs. Do not round until the very last thing. So that's why I'm keeping track of that by underlining. Alrighty. Now we can just have our 0.12499 mole of hydrosulfuric acid, divided it by our amounts of milliliters, and then convert milliliters to liters. Milliliters goes on the top to cancel out the denominator. 1 milliliter is 10 to the negative 3 liters. So this concentration should be and our calculator 6.249 molarity. And since this is 2 sig figs, this is 4 sig figs, our answer should be rounded to 2 sig figs. So 6.2 molarity of H2SO4. Always box in your answers, and that's all of our free response questions. Again, just to reiterate, if you're struggling with balancing equations, that is the first thing I would start tackling because it is so essential to manage your time for this exam. Furthermore, if I see a question like this and it's not like a combustion reaction or acid-base reaction where I can balance it pretty easily by using some tricks, I'm just going to skip it, save it for last, because this question is only 5 points. And if I was doing it chronologically and I ran out of time on this question, I lost 4, 5, 8. I lost 17 points. That's basically almost 2 letter grades just because I was so hyper-focused on this question. I would much rather lose 5 points than 17 points. Alrighty. Now, going to all the questions, multiple choice questions. Question number 1, we have aqueous sodium chloride and liquid bromine are formed. Keyword is formed by the reaction of chlorine gas and aqueous sodium bromide. So, sodium chloride and liquid bromide, which, by the way, is a diatomic element, are formed. So these are going to be our products. If I see these products in the reactant side, that is immediately wrong. So answer choices B and D are wrong. And furthermore, I'm looking at the formula for these. NaCl and NaCl2 are not consistent, so also answer choice A is incorrect. Now, let's look at our reactant. We have Cl2 gas, which, by the way, diatomic element, and aqueous sodium bromide. So I see in answer choice C that we don't have chlorine in our diatomic form. So process of elimination, that brings us to answer choice E. Alrighty. So what is the lesson from this question? Remember our diatomic molecules. This is also something that you can write. I remember Brinkhoff. So these are all of our diatomic molecules, and their name is Brinkhoff. For bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Okay, question number 2. Asphaltene is a large molecule found in crude oil. If asphaltene is burned in the presence of oxygen, what are the products? So I see a hydrocarbon. I see that it reacts with oxygen. Immediately, bells should be ringing. This is going to be a combustion reaction. And in any combustion reaction, that always forms carbon dioxide and water. Water specifically in a gaseous form because combustion reactions are very hot. And just a side note about combustion reactions, it's not only hydrocarbons, but it can also be some kind of form of alcohol. So like ethanol, butanol, those kinds of molecules are also going to go under combustion reactions. Alrighty, number 3, we have the balance reaction or balance equation, If 4.9 moles of O2 react, how many moles of NiS must also react? This is just simply using our stoichiometric ratio. So we have 4.9 mole of O2. Looking at our stoichiometric ratio, 3 mole of O2 is going to react with 2 mole of NiS. Put that in my calculator real quick. That is 3.3. Cool. Number 4, consider the following balance equation. We were given this. Calculate the number of grams of iron sulfide that will be produced when that many moles of S8 it reacts with excess Fe. Okay, so basically all we need to do is start with our beginning product, convert it into moles using our molecular weight. Then, since this is an excess, we don't really have to consider this. We use the stoichiometric ratio of S8 to Fe2S3 to figure out how much moles we get, and then use finally that molecular weight of Fe2S3 to figure out how much grams we have. So let's write all that information that I said down. S8, we have 256.48 S8 grams, 1 mole of S8. Then using our stoichiometric ratio, we can convert moles of S8 to our product. Then 1 mole of our product is going to equal to its molecular weight. I'm just going to abbreviate it as P for respect of time. Throw this in my calculator real quick. This is going to take a hot minute. Alrighty, I got 13. Cool. Wait, let me double check that. Yeah. Well, it's 2.5 or 12.5, but remember we have two sig figs here, so 12.5 rounded up will be 13. Alrighty. Consider the following balance equation. We're given that if 5 moles of zinc sulfide react with 6 moles of O2 according to this reaction, what would be the limiting reactant and why? Alrighty. I'm just going to look at the answer choices and see if we can eliminate anything. And immediately we can eliminate answer choices A, B, and C. And the reasoning is the definition of a limiting reactant. A limiting reactant basically limits the amount of product that we can make. So a limiting reactant is not because it has a smaller coefficient or it has fewer moles or has a larger coefficient. It is entirely dependent on how much moles of product it generates. So just by using our stoichiometric ratio, if I'm looking at 5 ZnS, I'm not even going to write moles just to save some time here. 2 mole of ZnS is going, let's just take ZnO, so 2 for 2. We have 5 molar product. Then for oxygen, 6 mole of O2, 3 mole of O2 generates 2 of O2. So our limiting reactant would be oxygen in this case because it generates 4 mole of our product. Cool. Continuing on. Which of the following statements is false about the limiting and excess reagents? So let's see. Limiting reagent of a particular reaction will never vary. It will always be the same regardless of the specific starting amounts used. That makes no sense at all. Because if we're looking at this previous question, let's say if we started with, I'm just going to use a large amount, 100 moles of O2, we're going to generate way more product than that 5 moles of ZnS. So the starting amount of product actually does really depend on what is going to be our limiting reagent. So this is going to be false, but let's look at all the other ones and just double check. If there's only one reactant present, then it's automatically the limiting reagent. That's true. If the limiting reagent is the reagent that's C, the limiting reagent is the reagent that is completely used up in the reaction. That is completely true in that previous case. If we had both of these, all the oxygen would be used up and we would have some excess ZnS. It is impossible to solve for the limiting reagent without having a balanced equation. That is so true. We could not figure out this without using our stoichiometric ratio to figure out how much product we're getting. Then, the theoretical yield of the reaction is based on a stoichiometric conversion from the starting amount of limiting reagent. Yep, that is true. Cool. Question number 7. A student in a lab conducts an experiment and collects 2.3 grams of product. She had calculated the theoretical yield of the product to be 19 grams. What was the percent yield? This is another thing that you can throw in on that little table to remember for the beginning of the exam to just splurge on the exam information sheet. Basically, percent yield is actual divided by theoretical yield, absolute values times 100%. And if I threw this in my calculator, 2.3 divided by 19 times 100 is 12.105, which for sig fig purposes, that rounds to 12%, which is answer choice C. Alrighty, number 8, which of the following statements about acid-base theory is true? So, statement A, in a precipitation reaction, a proton combines with a hydroxide ion. That's true. But let's look at, whoa. Precipitation reaction. That is true for acid-base theory in an acid-base reaction, but in a precipitation reaction, that may be the case, but may also not be the case. Then, a polyprotic acid would produce multiple hydrogen ions in a solution. That is true. An example of a polyprotic acid, we can think of sulfuric acid, H2SO4. This is specifically a diprotic acid. If we're looking at a triprotic acid, that would be an example of another polyprotic acid. Basically, polyprotic acids have more than one hydrogen to donate. Answer choice C, a precipitate is always formed in an acid-base reaction. Sometimes a precipitate can be formed in an acid-base reaction. That is used pretty commonly in as you're isolating some solutions in organic chemistry lab if you have to take that in the future. D, the oxidation state of atoms will change in an acid-base reaction. Nope. Not true. And HCl is a polyprotic acid. No, that is a monoprotic acid because there's only one hydrogen that can be donated. Alrighty. Number 9, which of the following has the highest concentration of protons? And we're giving all of these. First, determine if there's something that's soluble in water. In this case, silicon hydroxide or silicon hydride is not soluble in water. And if we're looking at our solubility rules, if my iPad can cooperate, most salts, salt. Oh, this is not even an ionic compound. These are two nonmetals with each other, so that would definitely not be soluble. That is a molecular compound, so this would not even generate any protons. Alrighty, now for the 2 molar of hydrosulfuric acid, since there's 2 moles of hydrogens produced by 1 mole of it, this concentration would actually be 0.4 molars. This is hydroxide, not protons, so this doesn't even produce any hydrogen. Since this is a monoprotic acid, that concentration of the overall solution should be the concentration of protons within that solution. And same thing holds true for this. So our answer choice, since this diprotic acid doubles the concentration of protons within that solution, since there's 2 protons in sulfuric acid, that concentration in reality for protons is going to be 0.4 rather than 0.2. So answer choice D is the correct one. Question 10, which of the following compounds would combine with water? Which of the following would not conduct electricity? And basically, this is just checking your solubility rules. So let's do it. When I'm checking my solubility rules, I just go sequentially from top to bottom. So let's look at nitric acid. Most nitrate, chlorate, and acetate are soluble. No exceptions there. So that's going to be an electrolyte. Magnesium bromide. Most chloride, bromide, and iodide salts are soluble with the exceptions. Always look at the exceptions. Always, always, always. Salts containing silver, lead, and mercury. Since this is magnesium, we don't have to worry about that. Alrighty. Most sulfate salts are soluble, rule number 4, except with calcium. Since this sulfate has calcium, it's not going to be soluble, and since it's not soluble, it's not going to conduct electricity within water. But let's check all of our answers just to be 100% sure. Barium hydroxide. Most hydroxide salts are insoluble. However, if we have barium, it will be soluble. Then ammonium chlorate. Ammonium chloride. Most ammonium cations are soluble. No exceptions there. So answer choice C is going to be our answer. Cool. Number 11, which of the following compounds is not characterized correctly? HCl, that is an acid that's soluble in solution and can donate a proton. NaCl is neither a base nor an acid because it doesn't have hydrogen or a hydroxide. We haven't covered any other forms of acids. So for Gen Chem 1, we're only looking at hydroxide and hydrogen cations, aka protons. I see OH, that's a base. I see CH4. CH4 is methane. This is a molecular compound. It cannot dissolve within water. So it's going to be an acid. Then I see OH here, soluble in water. That's a base. Alrighty. Number 12, what precipitate is formed from the reaction between aqueous sodium bromide and aqueous sodium magnesium sulfate? Basically, a precipitate is something that's not going to be soluble. So let's see if there's anything soluble within our solubility rules. I've written out the formula here. You don't really have to balance it for the purposes of this question. So let's just dive into the solubility rules. Alrighty, most chloride, bromide, and iodide salts are soluble for rule number 3, with the exception of silver, lead, and mercury. So this one's going to be soluble. And then sodium sulfate, most salts of alkali metals and ammonium cations are soluble. So this is also going to be soluble. So, since there's only soluble compounds in our reaction or in our products, no precipitate is formed. Alrighty. Number 13, what is the molarity of lithium ions in a 2 molar solution of lithium carbonate? So, if we're looking at lithium ions, let's triple check that this can dissolve. So going back to our solubility rules for the millionth time, we're looking for carbonate and lithium. And since lithium is an alkali metal, it's going to be soluble. Since in 1 mole of lithium carbonate, there's going to be 2 mole of our lithium ion. This concentration will be doubled. And to show it in a dimensional analysis way. 1 mole of the lithium carbonate generates 2 moles of the lithium, which doubles that concentration. Yep. Answer choice D. Alrighty. Number 14, what are the spectator ions in the reaction between aqueous hydroiodic acid and potassium hydroxide? So, when we're looking at the actual reaction, this is an acid-base reaction. Forms water, and it forms potassium iodide. If you remember, potassium is going to be one of our alkali metals, which are generally soluble. So, since Ki is soluble, in reality, they're going to be floating in solution as the potassium and iodine ions. And the reason why we call these spectator ions is because they don't form any bonds. They just exist floating in solution as ions. Okay. Number 15, 120.38 grams of magnesium sulfate was dissolved in water to make a final solution volume of 0.5 liters. What is the molarity of the magnesium sulfate solution? The molecular weight of magnesium sulfate is 120.38 grams. You can just figure this out by looking at the periodic table and just adding up all these individual molecular weights to add up to 120.38. So 128.38 grams, converted that to moles, that's just 1 mole of MgSO4. Divided by 0.5 liters, because that's what molarity is, moles over liters. This is going to be a 2 molar solution. Number 16, which of the following represents a net ionic equation? Net ionic equation, basically, we're not looking for any ions or aqueous components in either the reactants or the products. So for answer choice A, I see aqueous, aqueous, aqueous. Especially in the products, these will be spectator ions. A net ionic equation will only look at the floating ions in the solution within the reactant side and only look at how they form that solid precipitate. B will be a net ionic equation. While it doesn't form a solid precipitate, we have the proton and the hydroxide floating within a solution, and it forms water as a liquid. There's no spectator ions floating in the product side, or there's no spectator ions within the reactant side that does nothing. So this would be a net ionic equation. Then, answer choice C, we have spectator ions floating in solution doing absolutely nothing. This would not be a net ionic equation. Which of the following statements about oxidation numbers are true? Answer choice A, oxidation numbers are the same as formal charge. They are not. Basically, oxidation states is a form of keeping track of electrons within reactions, specifically redox reactions, while formal charge is keeping track of the charge of or relative charge of a molecule within a Lewis structure. They're not the same thing. B, in a compound, oxygen will usually have an oxidation number of -1. If we remember that little chart that you should have probably written down on your exam, oxygen will have a oxidation state of -2 within a compound. Any element by itself will have an oxidation state of 0. That is true. For polyatomic ions, the total of all atoms' oxidations should equal 0. If we're looking at a polyatomic ion, any ion, the sum of those oxidation states should equal the overall charge. So, for instance, if we had phosphate, all the oxidation states for oxygen and phosphorus should equal -3. And then for E, that's just looking at that table and remembering the rule that hydrogen will have an oxidation state of +1. Now, let's just apply these. We need to find oxidation number where sulfur is -2. This is +1, +2. So, basically, how I notate my oxidation states is pretty simple. I put the individual atom oxidation state on the top, and then the overall sum of that on the bottom. Since we're trying to equal 0 over here, this has to be -2. So, answer choice A is going to be correct, but let's just look at all the other ones. I see -1 for a total of -2. This has to be +1 because there's 2 of them. This is going to be -2 for a total of -6. This is going to be +1 for a total of +2. So this sulfur should be +4 to have a net charge of 0. Same kind of idea here. -2 for oxygen within a molecule. Since there's 3 of them, overall it's going to be -6. So sulfur needs to be +6 to have a formal charge of 0. Or, sorry, for all the oxidation states to add up to the overall charge in the molecule. +1, +2, because there's 2 hydrogens. -2 is going to be -16. Since there is, we have to figure this out real quick. This will be +7. Since there's these 2 sulfurs need to equal an oxidation state of +14. 14 divided by 2, each sulfur atom should be +7. And I'm just going to circle all the sulfurs. Well, answer choice A would be our correct answer. Alrighty. If you have any questions about exam for material, please email me. I will be sending out a Canvas announcement that my office hours will be canceled for Monday and Tuesday, unfortunately, due to dental school interviews. I am sorry if that has inconvenienced you in any sort of way. As trying to make this up to you, if you need my office hours, please email me with a couple of times that you can meet throughout the week, and we can see how that works within our schedules and meet up during that time. Thank you so much, and have a great day.